Good afternoon, and welcome to John Conway Separated Seminar Series. And today's our speaker is Jacinta Torres, and she is associated with the Jagiellonian University in Krakow, Poland. And she is her area of interest is area of research is intersection of representation theory, algebraic combinatorics, and geometry. And she is also leading a grant which is called Sonata, algebraic combinatorics and geometry in representation theory. And thank you so much for accepting our invitation, Jacinta. So over to you. And she is talking about today about the atoms and charge beyond type A. So please
Thank
go ahead.
you. Thank you so much. Thank you so much for the invitation. It's a pleasure to speak here. So yes, I will speak about atoms and charge beyond type A, and hopefully by the end of the talk, you will know what these things mean. So, okay, let's start. Click on OK. Oh, okay, there we go. Oh, no. Sorry, I think I have to go to the slideshow. Yeah, okay. So our story starts here with a complex semi-simple Lie algebra G and two dominant weights. So we are assuming here that we have a choice of maximal Cartan matrix and two dominant weights with respect to the choice of a Borel subalgebra. If you want to think of a particular example, you can always think of traceless matrices of size n times n. This is SLN. And then dominant weights are in one-to-one correspondence with partitions which have at most n-1 parts. So one can, especially if you like combinatorics, you can definitely think about it like that, although that's what we call type A. And this talk is actually about going beyond type A. So you can think that for beyond type A, you have some Lie algebra which maybe is embedded inside of SLN, and then the partitions have some extra conditions. So one can think of it like that. Okay, so for some reason, there you go. Okay. So given these two dominant weights, we want to look at V lambda, which is the representation of G of highest weight lambda. It's finite dimensional, irreducible. And we look at the mu weight space of that, and then take the dimension. This is a very famous number. It's called the Kostka number. And we will be talking today about what are called Kostka-Foulkes polynomials, which are Q analogs of this number. So what this means is that, well, this is a definition of them. Here we have a sum over the Weil group. This is W, and in the case of SLN, this is the symmetric group, and here is the sign of a permutation. So this means like -1 to the length, right? So this is the sign, and here we have PQ, which is a Q version of Constant's partition function, and maybe I should not say too much about this. It's a little bit technical, but the constant partition function tells you how many ways a particular weight can be written as a sum of roots. So, okay, so let's continue. Oh yes, and what does it mean to have a Q analog? It means that when you make Q equal to 1 in this formula, then you get back d lambda mu. So that's what it means to have a Q analog. And we are going to be focused on this particular Q analog. And if this definition seems a little bit confusing or, I don't know, maybe random, so then hopefully the next slides will kind of make it seem less so. So here are some different incarnations of these polynomials, Kostka-Foulkes polynomial K lambda mu. So first of all, many people know them at first as Kostka-Foulkes polynomial, including myself. So they arise in the theory of symmetric functions as change of base coordinates between sure functions, which are here on the left S lambda. They are indexed by partitions, and the whole Littlewood functions, which are on the left, on the right hand side, sorry, this P mu xq. Okay, so these are two known bases of the ring of symmetric functions, and the change of coordinates coefficients. These are precisely our polynomials. All right, so let's continue. Another incarnate.
Sorry.
Yes.
What is P here?
P are the whole Littlewood polynomials.
Okay.
Yeah.
Very good.
So it's like the whole Littlewood
Thank
basis.
you.
Yeah. And so another thing is that, okay, here, this formula, as I have written it, it is not necessarily only in type A. So this holds in general, except that if you step beyond type A, then this formula has another meaning, which is also in terms of, we could say, symmetric functions, but these functions live inside of the extended affine Hecke algebra. So this is like another kind of universe where they live, whereas in type A you can really go, do just symmetric functions and work only combinatorially. Whereas if you go beyond, you have really way more structure. But then the original symmetric functions also appear there. So it's like a natural generalization of them. Okay, so what else are they? This is, they appear as jump polynomials of the Berlinski filtration. So this is some filtration of V lambda, which was made by René Berlinski quite a while ago. If I'm not mistaken, it's already been like 35 years that this filtration was made. And so this, maybe I didn't write this K lambda mu Q equals, but this is what they are, this sum. So, and these jump polynomials, what it means is that, okay, here this JPE, E is some idempotent, some nilpotent element, and this space here is the space where E to the P plus 1 vanishes. So that's what it is. So that's definitely a very nice interpretation. In particular, we can already see from this jump polynomial description that these polynomials have positive coefficients, right? And another affirmation, which implies exactly the same thing in a different way, is that they are also Kasdan-Lustig polynomials for the extended affine Hecke algebra. And so this kind of ties up with the first thing that I said, because these two things are very much related. So if one wants to develop this theory, one needs both things, and one can prove both things in the same context. And this is done in a really nice preprint by Kendra Nelson and not preprint, sorry, overview paper, Kendra Nelson and Arun Ram, which I very much recommend to read. Yes, and then this last part about Kasdan-Lustig polynomials, this is very much the work of Kato and Lustig. So let's continue. So now we have introduced the problem, and the problem is to find a positive combinatorial formula for K lambda mu. So one could say, in fact, like, why is this one, this jump polynomial, why is this not a combinatorial formula? Well, I don't know, but let's say what we mean by a positive combinatorial formula. This is like precisely means this, okay, for us in this talk. Yeah. So here is already a typo. I'm very sorry about this. So this amounts to finding a set B lambda mu of cardinality. This should be D lambda mu. Okay, so this is this D from the beginning here. Tick this D lambda mu. So we want a set which parametrizes this weight space. Okay. Right, what else? We want a map which assigns to each element in our set a positive integer. And here again, another typo, this should be greater or equal to 0, yes, such that our polynomial K lambda mu can be written like this. So this is like a generating function over this set with this function. So that's what we mean by a positive combinatorial formula. We want really a set which we can get our hands on, and we want a function which we can compute, preferably in an algorithmic way, but you know, any function will do as long as it's very precise. And we call such a map a charge statistic after Lascaux, Schutz, and Berger, who solved this problem in 1978 for type AN. So this means for SLN plus 1. That's right. So now let's talk a bit about that. Well, first, I will also recommend this really nice memoirs book by Lynn Butler. So if you want to read about this is very, very beautiful math, very beautiful combinatorics. Okay, so here is an example. It's kind of supposed to speak for itself. And in it, I will talk to you about some of the parts which appear in the previous slide. So first, let's just look at what's written there. We have this kind of graph, right? So in fact, in a moment, I will tell you why this is like half a graph, but let's just look at the graph first. At the top, there is just one vertex and it's labeled by a tableau. So these guys, in fact, every vertex should have a tableau, but I have only drawn the tableaus at the very top and at the little kind of bits at the bottom, the little fringes at the bottom. And so these are semi-standard Young tableau. In general, if one has a partition lambda, one can look at partition lambda and an integer n, one can always look at the number of, well, at the set of semi-standard Young tableau with entries in between 1 and n and shape lambda. And so what does this mean? This means that you get your partition, you make a Young diagram. So in this case, you would have 2, 1, 1, 1, 1. Okay, so in general, that's how you construct it. You have a partition, which is a non-increasing set of integers, a sequence of integers, and then each integer represents the length of a row. You start from the first one and you work your way down and you align them all to the left. So that's a Young diagram, and you have to fill them in with numbers from 1 to n in a way that they increase, they mono increase in every row. So this means that there can be, 1, 1, such as here. And they strictly increase in every column. So that's that. And so what does this have to do with anything? The set of semi-standard Young tableaus of shape lambda is what we call a model for a crystal B lambda, which will in fact be the set we are after, except that we have to restrict ourselves to the elements of content mu. And this is maybe not super important to say it right now, but let's say that all of these guys at the very bottom, they have the same content. And you can see that because you have 1, 2, 3, 4, 5, 6 in all of them. So maybe let's just leave it at that. Yes, and what I have drawn here is actually half of the crystal of the adjoint representation of SL6. That's right, SL6. So, okay, so what do we have here? We have some edges and they are labeled by integers between 1 and 5. This is because it's A5, it's type A5, okay? And then at the very bottom, I have written this statistic. So it seems a little bit silly somehow to just write 1, 2, 3, 4, 5. I mean, it maybe will not tell you anything right now, but I can just quickly explain you kind of in general what is the idea. So if you look at these fringe little bits at the bottom of the picture, these tableaus, and you read their words, starting from the right and reading down the column. So this case is very easy, right? So if you look at the first one, its word is 6, 1, 2, 3, 4, 5. The second word is 5, 1, 2, 3, 4, 6. The third word is 4, 1, 2, 3, 5, 6. Okay, so and then we have to kind of count how many times we have to go back if we start counting. So what does this mean? let's look at the first word. You have 6, 1, 2, 3, 4, 5. So you look at where is 1 in the word, and then you put a 0 there. You look at where is 2. If 2 is to the right of 1, it still has a 0, and so on. And when you get to an I, such that I plus 1 is to the left of I in the word, then you have to add 1 to the index of I. And then when you finish, you add all those indices together, and that's your charge. So that's how to compute the charge of a word.
No veo a todos en tus contactos. ¿A
Oh,
quién se lo quieres enviar?
sorry, my Siri started telling me something and scared me. Okay, so yes, so that's how you compute the charge of a semi-standard Young tableau with this weight. In general, it's a little bit more tricky, but it's actually very similar. You just have to extract words. And so let's do another example. Let's do 4, 1, 2, 3, 5, 6. Okay, so yeah, unfortunately, I'm doing the talk on slides and not with something to write on, but maybe you can just like really use your imagination and just write it down maybe in your paper, 4, 1, 2, 3, 5, 6. And so now let's look at where is 1. So let's write a 0 next to it. This is its index. And then let's see, where is 2? Well, it's to the right. So let's add 1. Let's just also put a 0 on it. 3 is also to the right of 2, so it also has a 0. But now 4 is to the left of 3, so we add 1. So now 4 has a 1. And now let's look, where is 5 with respect to 4? It's to its right, so it has the same index as 4, so it has 1. And now 6, same story. It's to the right of 5, so it also has a 1. So we have 3 numbers labeled by 1, and all the rest of the numbers are labeled by 0. So when we add all of those numbers, we have 3. And that's exactly the charge of this middle tableau, which appears there. So that's how you do it. And if you have a more complicated word, that's how you do it too. You just start from 1 and continue until you get to n. So that's how you do it when you have a word which is a permutation. All right. So yeah, so this is kind of what the story looks like in type A. The classical exponents means that we are in this specific case where the entries are really from 1 until n. Yeah, and maybe let's leave it at that for now. And yeah, the problem is just completely solved. There are some other interpretations of this function. In particular, in 1995, notably, Lascula, Clerc, and Thibon re-described this function, which seems very combinatorial and is somehow very nice, but it's like, where does it come from? They interpreted it in terms of crystal operators, which is this graph structure. So they use the graph structure, the crystal graph, to precisely represent this function charge. So this is what they did. And okay, now let's go to beyond type A. And so in type CN, so this means the symplectic Lie algebra, there is a conjecture due to Cédric Lecouvé, which he made in 2005. In this case, he formulated it in terms of something called Kashiwara-Nakashima tableaus, which look very similar to the tableaus that we have shown, except that they are just more tricky. They have more conditions on which letters can appear or not. And yes, the combinatorics are way messier. And representation, theoretically, it's a much harder case because it's not simply laced. So not all the roots are conjugate if you are familiar with root systems, and it's that's the reason somehow. And okay, so we proved this conjecture with Maciej Dołęga and Thomas Gerber some time ago already. Yeah. But only for the case of lambda equals k times omega 1. And what this means in terms of combinatorics is that we proved it for the case of one row only. So a tableau with one row, and that's the only case that we showed. And it was like 40 pages. It was quite a complicated calculation, and we had to figure out some really pretty, actually, combinatorics around it. But okay, so far we didn't get further than that. We haven't really worked on it for a while now, but I think it's a really nice thing to do, and I would really like to still be able to prove the whole thing one day. But okay, so other approaches, which might, you know, because this is very type CN specific, so you could be like, okay, so what else? Well, there is also Leonard-Lecovay's formula for generalized exponents, but for type CN. So they have a formula for all the, for all the generalized exponents, but with this restriction on the mu. So the mu is what we call the zero weight. Yeah, and so by the way, before you might be confused, like, oh, but that was not zero weight because it was like 1, 2, 3 until n. But that's because we're dealing with traceless matrices, and these numbers, they kind of correspond to they correspond to the fact to the diagonal entries of the torus. So that's why it's like that. So when you have 1 until n appearing there only, then that means that it's 0 because of the trace 0 condition. And okay, so they have another formula. Okay, it also unfortunately doesn't really generalize to other weights even. So there is not a conjecture which generalizes this, but it's a very nice formula. However, you know, it doesn't go further than that. Okay, so then there was some new hope I wrote here 2023. I think it's published already, but I'm not actually sure about this. But in any case, it was actually posted on the archive in like 2020 or early 2021. And this is a really, really nice work by Leonardo Patimo. He did another oh, by the way, sorry. So let me just say one thing, that this first description I wrote, La School Leclerc-Thibon, it somehow seemed to give a lot of hope to a lot of people. At least this is what my previous advisor, PhD advisor, Peter Litterman, told me once. He said that everybody thought that this was going to be the way to generalize these two other types because this was using the crystal structure. But it turned out that when you try to do the same thing, it just doesn't work in other types at all. So unfortunately, that didn't work. And so okay, so now this is like some new hope in the same way, really, because what Leo did is that he has its alternative description of the same charge statistic in type A, but by translating the problem of finding the charge onto the affine Grassmannian. And I will tell you a little bit about how this story looks like today, just like in a moment. Yeah, we still have quite a lot of time. So, okay. So basically, that's where the title of the talk comes from, because a charge statistic actually can be deduced after finding something called atoms and swapping functions that mimic combinatorially wall crossing for hyperbolic localization. And okay, the approach is type independent, but when one constructs the so-called atoms, and these are like certain slices of your crystal, so in the case of here, this would kind of correspond to picking in a clever way each of these elements, these 1, 2, 3, 4, 5. So in general, this looks more complicated, but the idea is to have only one guy per weight in your atom in a nice way, which I will not go into details right now, but okay, so this is a type-independent approach, but the construction of the atoms is not. So this is like, again, I mean, it's not, the construction of the atoms is not type-independent yet, maybe there is some way to do it type independent, but somehow so far we have no idea really. It seems like the construction of atoms for now is quite type independent, but yeah, one can follow this general approach. And we did it for type C2. We are working on the general type. It's more messy. Leonardo had a kid and you know, life. So we are working on type CN, but there was so much work already for type C2 that we put it out there. So hopefully this will be published not too long from now. Okay, and I will tell you a little bit about Patimo's
I have one
strategy.
question here.
Yes, yes.
What do you mean by type C2 here?
Oh, SP4.
Okay, SP4.
Yeah,
SP4.
SP4.
Thank you.
So really, you know, 4x4. Like
okay.
Yeah.
Okay.
Yeah, so this is a very little baby case. So in the thinking diagram is 2 vertices and double line in the middle with an arrow. This is that case. Yeah, somehow we feel like this should be the hardest part, but after all, it seems it's not completely obvious how to go out of it. Okay, so yeah, so here I already wrote SP4. So this is like the a little bit dense. So let me take you through it. This is about Leo's work. So this slide is really about that. And we look at the geometric side here. So we take, instead of G, a Lie algebra, we take a complex reductive group with a Langlands dual group G check. And so in this setting, this really means that we are taking SP4 as G and G check is SO5. And okay, so what the story looks like in a very kind of hand-wavy way is that for a regular co-character of the extended torus action eta, so eta is our regular co-character, extended torus means that we really add one C star to our actual torus, to our actual affine torus. Okay. Okay, and then we take lambda and mu as at the beginning. Just 1 second, I'm just letting some people in. Okay. Yes, so lambda and mu as in our setting. And mu is less or equal to lambda, just so that everything makes sense. Then there is something called the hyperbolic localization functor. Which goes from the derived category of Tx, this extended torus, equivariant constructible sheaves on something called the spherical Schubert variety, which is indexed by lambda, with Q coefficients. And then this dB of a point is the derived category of sheaves on a point, which is equivalent to the category of graded Q vector spaces. And okay, so what this like actually means is that you are taking here some constructible sheaf, and you are like, let's say you take the simple object IC lambda in the left-hand side category, and this is sent to the weight space V lambda mu. That's what it means. For a specific region where eta should lie. So this is what I'm gonna tell you a little bit about in the next slide. So if eta would be dominant as a co-character, but without the extended part, then that what I just said, that's what it would mean. And let me see, did I put this later? Yeah, sorry, this slide should have been before. So if eta is dominant for the finite dimensional torus, then the hyperbolic localizations are the weight functors. This is what I just said, that they send an intersection cohomology sheaf IC lambda to the weight space V lambda mu, which is, yeah, the weight space for the irreducible highest weight module V lambda. And in this case, we say that eta is in the MV region, where MV is short for Mirkovich-Vilonen. And okay, if eta is affine dominant, on the other hand, so this means that the pairing between eta and any positive affine root is positive, then the hyperbolic localization functors return certain graded vector spaces whose graded dimensions are these renormalized Kostka-Foulkes polynomials. So in this case, we say that eta is in the KL region. This means Kasdan-Lustig region. And these terms were kind of coined by Leo in his work. Yeah, and so one can define the graded dimensions of the images of these HL eta mu functors evaluated on the simple object IC lambda, and call them renormalized eta Kasdan-Lustig polynomials. So they only are the Kasdan-Lustig polynomials when eta is in the Kasdan-Lustig region. And we say that a function going from B lambda to Z is a recharge for eta if one can have such a formula as is written on the slide. Okay, so now, yeah, I will kind of go back here and say something about the hyperbolic localization property. So what do we have right now in the story? We have this hyperbolic localization functor that somehow gives us the polynomials that we want as Poincaré polynomials of our vector space when eta is in this Kasdan-Lustig region. And when eta is in the MV region, they are somehow really easy to compute. And so what happens in between these regions? So it turns out that these regions are separated by some hyperplanes. And actually, like what actually happens is that hyperbolic localization only changes value when you cross one of these hyperplanes. So there is a simple rule to compute the hyperbolic localization functor after crossing such a wall. And it's like this. So here are these formulas. So basically, we denote our hyperplane by H lambda. It's separating two co-characters, eta 1 and eta 2. Let's say that eta 2 is lying on the positive side. And then what Leonardo showed is that we have for the reflection of mu with respect to the hyperplane, if this condition holds here, mu less than eta less or equal to lambda, then this is how to compute them. And so this kind of, if one sits down and thinks about it for a while, then this kind of solves the problem if one can find something called a swapping function. So let's see. Yes, so here it is. So to track these changes combinatorially, one must construct something called a swapping function, which is a function which goes from B lambda mu to B lambda S alpha of mu, well, S alpha check, which satisfies this condition that the recharge for eta 1 applied to an element in B lambda mu minus 1 is equal to when you apply it to the image. And having such a swapping function, we can then derive R eta 2 from R eta 1 by swapping the values as indicated by the swapping function. So these swapping functions are an essential ingredient to perform wall crossing combinatorially and to modify the trivial recharge in the MV region, which is what I said at the beginning, that it's very easy to compute it there and to manipulate it until you get to the desired recharge in the KL region. So let's go. Yeah. So in type AN, swapping functions are given by modified root operators, which are defined for any positive root. And this was defined actually by quite a few people, let's say Leonard, but this was already originating back to Littleman too, but only for type A. And okay, here we have the definition of the charge statistic again. So another formula for it in type A. And yeah, so this EK alpha, this is like, you know, the root operator corresponding to alpha. So how, and oh, in the graph before, these E's can be seen as the arrows. So these arrows that I drew, they were like the opposite direction of the E's, but okay. So this is what it means. And our main results consist of atomic decomposition of the type C2 crystal. So, well, actually, Leonard, Lecouvé, they already had atomic decompositions for the type A crystals. Leonardo obtained a different decomposition, well, the same decomposition in a different way, and then showed this formula here. So he showed that this formula here is exactly the one that we already knew, but in fact, he proved it by the equality with the Leclerc-Lascaux-Thibon formula. And what we have done is we have mimicked this for type C2 by constructing atomic decompositions of these crystals. This was much harder than for type A. And then swapping functions. This was maybe even harder than the actual atomic decomposition for many technical reasons. And as a byproduct, we obtain this statistic, which is written right here. And so you can see that there is one epsilon with a hat, and there is a comment about this. It says, okay, this epsilon with a hat is not attached to a modified crystal operator, but rather it depends on the atom in which T sits. So this seems very obscure, but yeah, it's somehow not so obscure. It's yeah, maybe. I mean, it's not gonna be the same as in type A, that's for sure. So yeah. So anyway, this is kind of what our formula looks like. I wrote it in this way because that's kind of in analogy to the previous formula for type A. So this is like looks very, very similar, the sum to this sum. But one can write it in also kind of ways which more exhibit the actual atomic decomposition, I think. Yeah, so thank you very much for your attention. I think I was a bit quick, but then maybe there is some time for questions.
Thank you. Thank you so much for a nice talk. Is there any question from the audience? Okay. Okay, I have a different aspect of because you are just describing all the setup in representation theory part.